Welcome back. Today I want to talk about model specification, which is a topic very frequently ignored in textbooks. The key question I want to answer is whether the model you use is the correct model to describe your data. Or put differently, is the model you estimate the best model you can obtain? Now, the main aim of this session is to think very carefully what is meant by the best model. Yeah, so what is the best model for your specific requirement? And also, what's the process of actually getting to that model? Yeah, so in previous sessions we always did some regression analysis, but how did we come up with the different variables we used? Yeah, what is the right approach to empirical modeling? Should you just do kind of a trial and error? You just throw in some variables randomly and you see what works? Or is there some further logic to it? And you can even go further that, of course, you can abuse statistics. Yeah, so put differently, if you throw out important variables, as we know, you might end up having a biased model. And we spoke about the omitted variable bias as one example. So we have to think very carefully if we work in particular with secondary data, where we don't control the data collection, where there is lots of potential issues occurring, such as measurement problems and so on. We have to think very carefully how we do model specification in this setting. The first thing to understand is what does it mean to talk about a best model? Now this depends very much on what's the purpose of your analysis. Yeah, do you want to forecast, for instance? Do you want to make predictions for the future? In this case, you have to ask yourself, what's your time horizon? Is it short, long-term forecasts? In the case of forecasting, the main focus is how good is your ability of forecasting. The main focus is not necessarily to identify individual drivers. The other thing is sometimes when you make these binary choice models, and we discussed them before, the issue there is what is an acceptable level of error. We talked about different types of errors, and of course one error is simply you're not able to detect a certain characteristic. But the other type of error is you might have a false positive. Yeah? You might think something is happening, but actually nothing is happening. So you have to think carefully, what are acceptable levels of error? Sometimes your main purpose is indeed you try to understand underlying drivers. You want to really know, okay, is now, for instance, firm size affecting profitability, and by how much? So in this case, we have to be more careful about issues such as multicollinearity that might affect your ability to detect individual drivers. Put differently now, how can we get started? So in my opinion, the best approach is usually to think from a theoretical perspective. Now, theory does not always have to be a fancy mathematical model. Yeah, so very often what I do first is I simply try to relate different variables. Yeah, so very often I just simply draw a picture. And I ask myself, how are these different components interrelated? Are there any things in between? Are there any effects I have to consider when I consider this relationship? Is there any moderation going on? What always helps, in my opinion, particularly when you do this for an academic research project, you have to go into the literature. The literature will tell you very much what is the starting point of a good empirical specification. So what usually works quite well is you take an existing empirical paper, you check out their model, and you start actually replicating that. And then you might maybe add a few more variables, and you might then make an argument that actually these additional variables add explanatory power to the model. and hence this is an important contribution. End of the day, it's all about testing, testing, testing. We have done lots of testing in this course, and that's actually at the heart of model specification. I always encourage people to be very honest about this process and also show the different steps in your analysis, not only the final outcome, but really demonstrate what are the steps you have taken to actually derive this final amazing model that works very well. There are two very useful methods to derive this perfect model, so to speak. One approach is to use general to specific. So the idea is you start with a model that has all the bells and whistles inside, so you include as many variables as possible. And then you try to test down the model. You try to reduce the number of variables, you kick out insignificant ones, and you test whether this reduction in your model, the simplification, is valid. Now this is quite a useful approach in many settings, assuming you have a sufficient sample. So it depends again on the circumstances. However, there's a tendency that you end up with a final model which might be slightly overcomplicated. That has ramifications. Yeah? So there are issues with complicated models if you have too many parameters. We talked about degrees of freedom before. There are other issues which we explore later when it comes to parameter stability, for instance. Now, the alternative is to go from a specific model, so start with a small model and add stuff to it. This is sometimes a good idea if your estimation procedure is not a straightforward procedure. So sometimes when I do, for instance, Bayesian statistics, where I have to rely on some algorithms to do the work for me, where quite often models might not actually converge properly. Starting with a simple model might not be a bad idea, and then adding complexity to it. The danger of this approach is you overlook important variables. So what we then do is we also, of course, compare model fits. Of course, we spoke about the R-squared, we spoke about the pseudo R-squared in the case of logistic regressions, but we have better measures, so-called information criteria. Information criteria are used to compare different model specifications. These comparisons are only really making sense if you restrict your sample, if you have the same sample across specifications. Yeah? Obviously, if you add more variables, it's very likely, due to missing values, that your sample size will go down. If you want to compare specifications, you have to maintain the same sample. Otherwise, you compare apples and oranges. In terms of information criteria, there are many of them, but we mostly look at the AIC and the BIC. The AIC, I will of course mispronounce, that is the archaic information criterion, is leading to more complex models, and you will see that in action soon. The BIC tends to get you to slightly simplified models, maybe sometimes oversimplified. So they don't always have to agree. The main purpose of these is as a measure of comparison between model specifications if you maintain the sample. That's important. And your main objective is here to minimize information criteria. Good, we now jump into Stata. And again, you have, of course, all the data available in GitHub. The link is down below in the description. If you have any questions, of course, you can always reach me. The best thing to do is to leave comments down below. And as always, if you enjoy this, if you want to have more data fun and for sure 0% entertainment, please like and subscribe for more excitement. Good, so what I have done here is I changed my directory. I opened the data set. It's about the US stock market. and I cleared to remove any data in memory. So I'm just now running this and look into the data. Again, I did not put in any descriptions, so I will talk about this very briefly. So you have monthly data, so here this is the time dimension, so we have here months, we have year, we have the stock market return, this is the S&P 500, then you have different macroeconomic drivers. So PI is a predicted inflation measure, so this is the expected inflation. UTS is the unexplained, so the shock in the term structure, it's the term structure of interest rates. Again, I don't want to go into the financy bit behind it. Again, if you want to know more, just leave a comment and I will get back to you. URT is the unexpected risk premium, so this is the difference between AAA rated bonds and BAA rated bonds. Then we have the unexpected inflation, the unexpected industrial production, and the unexpected oil price change. So these are basically economic shocks. So the idea is, can we explain the stock market return using these macroeconomic variables? And there have been a few papers that actually explore this relationship. Good, so the first thing I would do is I would declare now that this is a time series. Again, I do this ideally in my do file, so I just do a tset time. Not necessarily very crucial to do this, except you want to use time series operators, but we might. I'm not entirely sure whether we actually will. Then we start with a general model. So we start here with our general model, where we just simply throw in all the variables we have. So what do we do here? We do a general to specific approach. RM is for the market return, and then I just click in here all these different variables. So I throw this all together and put it into a regression model. We just estimate that and see what happens. What we definitely need to do is, after estimating this, we have to preserve the sample. So one way to do this is to simply predict residuals. So I can do something like predict R, res for residual. So we get residual predictions if we have observations. So we can use that to define a sample. So for instance, you can do a generate command, I call this sample equal to 1, if the residual is not equal to missing. Yeah, so exclamation mark equal to dot means not equal to missing. So I can then use the same sample for other specifications where I actually reduce the number of variables, which would usually increase my sample size. Okay, I'm just now running this and see what happens. So we have 337 observations, so that's good. And we explain not an awful lot, but again, of course, not a big surprise, because end of the day we talk here about stock market predictions. Honestly speaking, if I'm able to predict the stock market, I don't have to do this. Yeah, I don't have to be on YouTube. In fact, I would still be on YouTube because I have nothing better to do. No, actually, I quite enjoy it. Okay, so what else can we see from that? Of course, go back to our recording on regression analysis. We see that there are some significant variables here. There's one which is kind of a borderline, which is only significant at the 10% level of significance, looking at the p-value. And others seem to be not significant. Yeah? So now the idea of testing down is to eliminate these insignificant variables step by step. Before we do that, it would be prudent first to estimate store this, because we will refer to this later. So we do an estimates store. And what I would also suggest is to do a variance inflation factor test. Again, we have done this in the video on multicollinearity. So that's just checking whether there is anything going on with your variables here. You can clearly see that the variance inflation factors are quite low, definitely below 5. 5 is very frequently used as a cutoff point, sometimes even 10, which I think is a little bit too high. So there is no evidence of serious correlation going on between these shocks, which is anyway something you would expect because these are shocks. So these are unexpected changes except for the inflation measure. So nothing I would be concerned about. This is important to note because once you kick out one of these variables, if there is multicollinearity, this will have quite an impact on other p-values potentially. Yeah, so you have to be a bit more careful. But this is looking fine. So I start now kicking out variables. I would start with this one here because anyway that's insignificant, and I would start with this one, has the highest p-value. So let me just start with this one and check whether this is a valid way to do it. Good, so what I will do now is I go back into this, and I kick out the term structure, and then I use an if statement to make sure that it's the same data set. It's just a good way of doing it. So if sample is, if I can spell it, equal to 1. Good, again I do an estimate store, and I do an estimate store B in this case, and then what I would suggest is I would suggest to do a likelihood ratio test. So LR test AB. So this is basically testing whether this restriction is valid. That's a good idea to do, in particular if anything is going on also regarding multicollinearity. This is a good idea to try and see whether this restriction is valid. Alright, so it looks fine. Looking at the likelihood ratio test, you see that the p-value is certainly above 0.05. So restricting your coefficients, in this case just one coefficient, to 0 is cannot be rejected. Yeah, so the null cannot be rejected. So it's perfectly fine to kick out this variable. Good. And now we see there are still some other variables in here, for instance, unexpected inflation, which is insignificant, so we can just continue this game. Let's do it one more time. So I just copy paste that. I get now rid of the unexpected inflation. Again, I maintain my sample. I reduce that and I test against the original model. Yeah, so now I have two restrictions here, and I just see whether I can restrict further. Just run this, and yeah, that's fine. You can do a further restriction. Then I kick out the predicted inflation. So I do one more and estimate store D, and I do the predicted inflation, expected inflation. Again, compare this to my original model and reduce that further. And again, that's fine to do. And then there is maybe one more, the unexplained risk premium. So we can also try this. So we go one further, and so on. Yeah, and this is basically the process you would take if you do a general to specific. So that's the risk premium, and we just test that again and see what happens. And again, they would be fine. Now, actually, all the remaining variables are significant. Not much has changed to the adjusted R-squared, and that's actually the idea. Yeah, you try to reduce it without losing much predictive power. Then what I would do is, at the end of it, I would just compare these specifications in a table. Yeah, so we do the estimates table A, B, C, D, E. And we have star here, and then we do a fixed format. I think that usually looks quite nice with 3 decimals, and we throw in our statistics. I just want to check the information criteria as we discussed before, AIC, BIC. I'm just now running the whole file one more time. And we end up with this specification table. So this is also quite often what I do in my empirical work. I show different specifications let then also the reader know, okay, if I, for instance, in this case, reduce variables, I don't lose anything in terms of predictive power. Now let me have a look at the AIC. So the AIC, if you want to minimize it, you actually end up with the AIC in specification D. So you would minimize actually here. Yeah. If you look at the BIC, you see the minimum would be specification E. So they actually disagree, which is quite common. So the AIC would prefer a slightly more complex model, yeah, compared to the BIC. Very often I would discuss this and then I would tend to agree with the BIC because I want to have a simple model structure where you don't actually lose any significant predictive power. So that's all regarding model specification. I see you in the next one.